Welcome back to my rubber heart. Today we are exploring a fascinating branch of rubber technology, semiconductive rubber compounds. These materials sit at the intersection of flexibility and electricity, designed to conduct just enough current to do their job without behaving like a metal or a complete insulator. We will unpack how they are made, what kind of carbon blacks are used to make them conductive, how electricity moves through them, and why they are so essential in everything from power cables to anti-static equipment. Let's begin with the basics. What makes a rubber semiconductive? Most rubbers are naturally insulative, meaning they resist the flow of electricity. But if we carefully design the formulation by adding the right type and amount of conductive fillers, we can shift that behavior into the semiconductive range. This means we can create a rubber compound that has controlled, measurable level of electrical conductivity, typically somewhere between 10 to the second and 10 to the sixth ohm per centimeter. Now, the key player here is carbon black, but not just any grade. To achieve semiconductivity, we use highly structured, high surface area carbon blacks with strong electrical properties. The most commonly used grades include acetylene black, furnace black types like Conductus SC Ultra, or specially designed conductive carbon blacks like Ketjenblack EC600JD. What sets these blacks apart from the typical reinforcing blacks used in tires or seals is their high structure, meaning the particles form long, branched chains, and their low volatility and high purity, which ensures they don't interfere with the rubber's curing chemistry or degrade over time. Take acetylene black for instance. It's made by the thermal decomposition of acetylene gas in the absence of oxygen. The resulting carbon black has an exceptionally pure, graphitic structure with very high surface area and excellent electrical conductivity. It's used when you need low electrical resistance and stability over time, like in high voltage cable shielding. So how does this actually allow electricity to flow through rubber? The mechanism is called tunneling or percolation conduction. When conductive carbon black particles are added to rubber, they begin to form a connected network. Once enough particles are present and spaced closely enough, electrons can jump between adjacent particles, creating a path for current to flow. This critical concentration of filler is called the percolation threshold. Below it, the compound is still insulating. Once you cross it, you start to get a dramatic drop in resistivity and the material becomes semiconductive. The finer and more structured the carbon black, the easier it is to reach that threshold with less filler. Now, let's talk about where semiconductive rubber compounds are used and why. One of the most important applications is in medium and high voltage power cables, where you will find semiconductive rubber layers surrounding both the conductor and the insulation. These layers play a crucial role in managing the electric field within the cable. Without them, the sharp potential difference between the metallic conductor and the insulating rubber could cause electrical stress points, leading to partial discharges, insulation breakdown, and ultimately cable failure. The semiconductive layer ensures a smooth voltage gradient, dissipates electrical stress evenly, and prevents charge accumulation. This extends the service life of the cable and ensures safe, stable operation, especially under high voltages. But that is not the only place where you will find semiconductive rubber. In fuel and oil hoses, especially in aviation or petrochemical applications, a semiconductive inner liner is critical for static discharge protection. As fluids like gasoline or jet fuel flow through a hose, they can generate static electricity due to friction. If that charge builds up and isn't safely dissipated, it could create a spark, and that is the last thing you want around flammable vapors. The semiconductive liner safely drains the static to ground, preventing ignition risks. You will also find semiconductive rubbers in anti-static flooring, conveyor belts, footwear soles, and rubber rollers. Basically, everywhere that electrostatic buildup needs to be controlled. In electronics manufacturing, static discharge can damage sensitive components. In explosive environments, it can trigger catastrophic events. The role of semiconductive rubber in these settings is to safely bleed off static charge without compromising flexibility, toughness, or grip. Even in EMI shielding applications, especially in aerospace and telecommunications, silicon-based semiconductive compounds loaded with metal-coated carbon blacks or graphite are used in gaskets and seals to block electromagnetic interference while still providing environmental sealing. So, whether it's managing electric fields in a cable, preventing sparks in a fuel hose, or protecting electronics from static, semiconductive rubber compounds are all about controlled conductivity. They are engineered with purpose, using the right carbon blacks in just the right amount to hit that sweet spot where rubber can carry a little bit of current without giving up any of its mechanical performance. Thanks for watching my rubber heart. If you've worked with semiconductive compounds or have any questions about which carbon blacks work best for your application, drop it in the comments. Don't forget to like, subscribe, and hit that bell icon so you never miss an episode. Until next time, stay elastic and stay curious.